All right, so I'm going to talk about angular and linear speed. These are two types of circular motion that come up in physics as well as quite a bit in trigonometry that we're working on right now. The two formulas that you will generally see in a book, your angular speed, which is represented by the Greek letter omega, is going to be your theta divided by your time, and your linear velocity, v, is actually going to be your angular speed times your radius. Now, I'm not really going to use these formulas and make you have to be able to regurgitate these formulas. I'm going to kind of walk you through on how to actually find angular velocity, how to find angular speed, linear speed, and go from there. All right, so we don't really need these formulas because I'm going to teach you conceptually on how to actually do this. The example I'm going to use to show angular and linear speed and how they're connected is I'm going to use the Ferris wheel. It's something that we're all familiar with. We've either been on a Ferris wheel at some point in our life or we've at least seen a Ferris wheel. Well, the first Ferris wheel actually came out in 1893 at the Chicago's World Fair, and this was actually a point of national pride for the U.S. as we had a saying, the Americans had a saying, that we had to out-Eiffel Eiffel because Eiffel created the Eiffel Tower in Paris for the World Fair prior to the 1893 Chicago's World Fair. All right, so we know a Ferris wheel is a circle. That's a beautiful, pretend it's a perfect circle. At the highest point of the Ferris wheel for 1893, you were at 264 feet. So we're going to say the diameter was 264 feet. It took, as it was revolving, 10 minutes for one revolution. So it took 10 minutes for one revolution. All right, so I'm going to ask, what is the angular speed of the Ferris wheel in 1893? And if you were on a car right here and you were rotating, how fast were you traveling miles per hour? That's going to be your linear speed. How fast would you be traveling at this point in miles per hour as you're going around? Well, this is going to be a two-step process. The first thing I'm going to do is I'm going to find the angular speed. And what I need to do is I will need to find my revolutions per minute. And that's where this omega equals theta over time, your revolutions per minute. And well, every 10 minutes I have one revolution. So I can actually get, so this is not omega, this is not revolutions. But my revolutions, I can say there we went 1/10 of the way for every revolution per minute. So 1/10 of a revolution per minute. To find my angular speed, all I do is multiply it by 2 pi. That's it. Just 2 pi. Because for every single one revolution, there are 2 pi radians. So I do 2 pi, and this is radians per revolution. My revolutions cancel. Now, all I have to do is do 2 pi over 10 by multiplying. This gives me radians per minute. So this is my angular velocity, or my angular speed. Of course, we'd want to reduce this down to pi over 5 radians per minute, and that would be my omega. All you do is take your revolution per minute and multiply it by 2 pi, because it takes exactly 2 pi radians for one revolution. And if I know my revolutions per minute, I can easily get my radians per minute. All right, once I know my angular velocity, it's really easy to get my linear velocity or my linear speed. What I'm going to do is I'm going to take my angular velocity. So I'm going to find my linear speed, linear velocity. Really, I'm going to use these interchangeably. There is a small, subtle difference between the two. But for all practicality and purposes for how we're calculating it, we don't need to really worry about that subtle difference. It is technically a linear speed that we're finding, not a linear velocity. All right, so what I'm going to do is I'm going to take my angular velocity right here, pi over 5 times, or my radians per minute. Now I have to ask myself, what's a radian on this circle? Well, we learned earlier that 1 radian equals 1 radius. It doesn't matter how large the radius is, that's still going to be 1 radian. So the radius of the circle is 132 feet. So I can do times 132 feet, and this is going to give me 132 feet is 1 radian. My radians cancel for my units. So my velocity ends up being 132 pi over 5 feet per minute. Okay, so that's my velocity. Now I just want to convert this into something that actually makes sense. Because if you had tell me it's 132 pi over 5 feet per minute, that means nothing to me. But if you told me something in miles per hour, I have a good gauge on how fast that's actually going. Because of how often we drive, we think everything in terms of miles per hour. All right, so let's convert this to miles per hour. We have 132 pi over 5 feet per minute. Now we just do our basic conversions that we do in science class. Let's see, there is 5,280 feet per mile times, and there is 60 minutes per hour. My minutes cancel, my feet cancel, it leaves me miles per hour. Collect, multiply everything on top, so I have 60 times 132 pi divided by 5 times 5,280, and this will be miles per hour. And when we do this, we're going to get approximately 0.94 miles per hour. So you're actually not moving very fast. This spot right here, as you're moving around, you're only going about 0.94 miles per hour, not very fast at all. Which actually makes sense because the Ferris wheel is not moving fast. It's more of a spectacle to kind of look around. And you got to think, in 1893, if you could get up to 264 feet, this was the time that predates skyscrapers. The view was something nobody had ever really seen at that point. That's why so many people paid to get on this Ferris wheel. At 50 cents a ride, it cleared well over $1 million at 50 cents a ride. It could hold over 2,000 people at one time on it. In fact, the carts itself that held the people were train cars, were the actual carts that would hold people as it went around. They were actually pulling train cars. So that's angular linear velocity. I don't think it's terribly bad. To find angular velocity, all you're going to do is take your revolutions per minute and multiply by 2 pi, because 2 pi is your radians per revolution, because you have exactly 2 pi radians per 1 revolution. Once you have your angular, you just take your angular and you multiply it by the radius, because your radius is going to be 1 radian. Your radians cancel, and this is going to give you your feet per minute or whatever your units are going to be. I strongly encourage you that you do your math with your units so you can see that it works out, because everything should cancel the way that it canceled that I did. Hi, I'm Mr. Buzzard, and these videos are supplemental instruction for my students. If you found the video enjoyable, make sure you click the like button and click subscribe, as well as the bell for notifications to receive future videos on high school mathematics.